again. So shall we start chapter 7 of today's lecture? So before I start chapter 7, I feel a bit some addition concerning chapter 6. Yesterday we had discussed something, but I felt that a very basic thing is dB or dBm or such kind of scales. I felt some people are not so familiar to so-called electrical engineering or electronics field. So we often use such unit of dB or dBm in electrical engineering or so. But some people are not familiar to such kind of expression. So I'd like to briefly I should briefly review this issue. Yesterday we had discussed why each signal channel is plus 3 dBm and why total signal total power is 18 dBm. So some people are not familiar to such kind of expression, so I'd like to describe something about that. So, so dB scale, dB is often used in the field of electrical engineering also, and this means just relative value, relative magnitude of the number. So dB means, D means deci. Deci means you may know liter and deciliter or something like that. The unit is 10 times smaller unit compared to the original value. And B means bell, maybe someone's name, bell. Yeah? And bell means just 2 times, 3 times, 10 times, just a number, you may. So dB means, bell means a logarithm. Logarithm, x is number, and you will take logarithm of 10. And dash means that you must multiply 10. So 10 times logarithm x. This is the dB scale. For example, if x equal is 1, so log 1 is 0, so we say 0 dB. Right? If x equal to 10, logarithm 10 to the 10 is 1. So 10 cross 10 multiplied 1 is just 10. 10 dB if x equal 10. If x equal 100, x equal 100, 100 means 10 to the power of 2. So logarithm 10 to the power of 2 means 2, actually. 2 by 10, 20. Okay? So if we say 0 dB means just 1, same value, same amount of value. 10 dB means 10 times larger, or something like that. If this bottle is 1 liter, 10 liter is a bit strange, but 10 dB larger than this. And if we say 20 dB means just 100 times larger than that of something that compared value. Of course, if 1,000 times larger value, we say 30 dB. And the same thing, if x equal 0.1, what value in dB? Sorry? Negativity, that's right. Yeah, that's right. 0.02, sorry, 0.01. This is just, in other words, 100 times smaller. Minus 20 dB. Okay? Just 100 times larger, we say plus 20 dB. But if 100 times smaller value for minus 20 dB, like that. Yeah? So we see a dB scale in this handbook, often see. And next, we also see a unit, dBm to say a power of optical power, dBm. Do you know dBm? What's the difference between the dBm and the dB? This is just simple meaning that dB means just the relative value of something, 10 times, 100 times, or 1,000 times. So 10 dB, 20 dB, 3 dB, we say. And the merit of using such a dB scale is just you can change the multiplying calculation to the just some addition of calculation. For example, if you say 100 cross multiply 100, you can simply change the addition of 20 dB plus 20 dB, 40 dB. So this is the merit of using a logarithmic scale. And dBm means just simply this unit, as a reference of this unit, is just milliwatt, optical power, milliwatt. So we say, when we say not 0 dB, 0 dBm, if we say 0 dBm, this means just 1 milliwatt power. And if we say 10 dBm, not dB, dBm, that means 10 milliwatt. Yeah? And 20 dBm means 100 milliwatt. This is just dB or dBm. It's so often used in the field of optical communications. So I'd like to confirm these things before the tutorial. Thank you. Any questions? No? Sorry, I will give you during the coffee break time because my computer has some trouble now. Okay. So let's start chapter 7. So chapter 7 sorry, includes the optical systems design. So I will describe, first of all, generic description of system impairments and design. And then design for systems with without amplifiers, and then systems with optical optical line amplifiers. So many things we have to consider to design such kind of a system. And another content is forward error correction impact on optical system design. So you will see some duplication with the yesterday's chapter 6 presentation because we had to discuss so much about the forward error correction. So now you know much about forward error correction. So I think it's not difficult to understand this section. And finally, I will describe the so-called reliability consideration. Mainly, this is focusing on submarine optical systems. Yeah, this figure shows the so-called general description of optical transmission systems impairments. So, as you know, this optical amplifier system has a transmitter receiver, and the signal propagates along the fiber amplifier combination so many times. So roughly speaking, the impairments in optical communication systems or optical signal transmission is, we can say, mainly two factors. So waveform distortion, which distorts the waveform's digital signal. As you saw the yesterday's session. So eye diagram or waveform. That's eye diagram or waveform could be distorted by the fiber transmission. And another impairment is so-called noise increase. In optical amplifier systems, optical amplifier generates ASE noise, amplified spontaneous emission noise from each amplifier. So ASE noise will accumulate and degrade the optical signal to noise ratio. So this accumulation of ASE noise is so in proportion to the number of amplifiers and amplifiers gain. Okay, and also significant impact on the transmission fiber is fiber nonlinear effects. This is mainly consists of SPM or wave mixing or cross-phase modulation or something. And this also degrades the waveform of the optical signal. So you can receive so degraded waveform at the receiver end. And the signal spectrum, pure spectrum will be broadened by such fiber nonlinear effect. And fiber nonlinear effects also induce another kinds of noise. That is a phase noise, induced phase noise. That you can see it looks like an increase of noise, excess noise increase other than the ASE noise accumulation. So we call this is the fiber nonlinearity induced phase noise. So we will briefly review this kind of impairments in Chapter 7 for design of the system. This is a description in Chapter 7 of your ITUT handbook. So first of all, simpler case is the systems without line amplifiers. So in such a line amplifiers, without line amplifier, optical budget is based on optical power levels needed to give the required BER in the presence of the receiver electrical node. So in this figure, this system without line amplifiers means that transmitter and receivers are connected by only one fiber, no amplifier. In this case, dominant noise source is receiver noise. So this means that no amplifier noise, but receiver noise is problematic. And the minimum average optical power of the receiver must be greater than the minimum receiver sensitivity plus optical path penalty. We saw yesterday optical path penalty. We need at least the minimum receiver sensitivity to cope with the receiver noise. But in addition, we will incur optical path penalty. So we have to need some more power to cope with the optical path penalty, 1 or 2 dB. In addition to the receiver minimum sensitivity. Yeah? And for systems with line amplifiers, so optical budget is based on OSNR, optical signal to noise ratio, needed to give the required bit error rate. So this means this amplifier noise, accumulation of amplifier noise is much greater than the receiver noise. So we have to take care about this amplifier noise, not receiver noise. And we will need to consider this optical signal to noise, optical signal versus amplifier noise accumulation. So as I said, the dominant noise source is amplified spontaneous emission generated in the line amplifier rather than in the receiver. So the minimum OSNR at the receiver must be greater than the minimum receiver OSNR tolerance by the value of the optical path OSNR penalty. So constraints on the minimum optical power at the receiver input to ensure that the electrical noise in the receiver is small compared to the optical noise. So I mean just optical noise is much problematic than the receiver noise in the optical inline amplifier system. So this is a diagram for a single channel, single span optical system. So such power budgets of such single channel TDM systems are given in, for example, these recommendations. And the budgets for multi-channel optical systems, I mean a WDM system, is also described in those recommendations. And the majority of optical systems without amplifiers are single channel systems. This is not always true. You may use a so-called WDM system for a single span optical system, but it's not so popular, or it's not common. So that description means we don't see so many times that WDM system without amplifier. Sorry, this is the power budget for small. So power budget for single channel, single span system. This is just a power budget for the single span, single channel system. So as you see, you saw the last yesterday chapter 6, we can draw such a picture of power budget: maximum mean output power, minimum output power, maximum input power, minimum input power, and this is a receiver sensitivity. This is just a necessary power for receiver. And we need some power for optical path penalty, 1 dB or 2 dB, above this receiver sensitivity level. So we call this is the minimum input power we require. This is just an example of our 10G 80 kilometers system. And the criteria is, as I said, a bit error rate of 10 to the power of minus 12. Yeah. This is just a description of a maximum, minimum, the difference, something like that. And path penalty has to be, I have to consider this chromatic dispersion or PMD or something like reflections or something like that. So this is a limitation in a single channel, single span system, most simple system in optical transmission systems. So optical systems limited in transmission length by optical fiber attenuation can be operated with the use of optical amplifiers. So that means just simply if you want to transmit the signal longer, and the system is just a transmitter, receiver, and the fiber, if you use booster or preamplifier, you can extend the reach of the system, just simple thing. And optical systems are limited in transmission length by chromatic dispersion require dispersion accommodation process. That means that if the transmission distance of your system is limited by the chromatic dispersion induced impairments, that the waveform distortion or something like not power level or SNR, then you can use dispersion accommodation, means dispersion compensator, dispersion compensation technique. And this is just, for example, G.652 fiber has so large dispersion. And you cannot extend the transmission distance if you use such G.652 fiber in a 1,550 nanometers region. But if you use dispersion compensator to eliminate the dispersion of the fiber, you can have the so clear signal I, and degradation could be improved. Okay. So the parameters contribute to the optical path penalty, chromatic dispersion or something like that, as specified in G.659.1, describes the maximum path penalty 1 dB for low dispersion system. and 2 dBs for large, high dispersion systems. So the path penalties are not made proportional to the target distance to avoid operating a system with high penalties. Yeah, this means just penalty if 80 kilometers 1 dB penalty, but it doesn't mean 160 kilometers 2 dB. It's not a so general relationship. So this is a description about the chromatic dispersion penalty. So in general, chromatic dispersion contributes to pulse broadening and distortion in a digital signal. As you see that the chromatic dispersion broadens the signal waveform and degrades the eye pattern. So the optical spectrum of the source, each wavelength component has a different phase delay and group delay along the fiber, so the output plus is distorted in time. This means 0.659. This tells you that why dispersion distorts the waveform. As you see, that the signal pulse has many frequency components, and dispersion makes a difference of speed between these frequency components. So as a result of this process, the waveform will spread in time, and the waveform will be degraded. So the other cause is the modulation of the source. So Fourier frequency content of this as I described, the signaling that can be compatible to the extent. And sometimes chirping occurs in source wavelengths, and this could change the situation of the pulse broadening of the waveform, signal waveform. This is just an example of a maximum chromatic dispersion penalty. So you can see that this no chirp with no chirp and energy signal. Here you see 2.5G, 10G, 40G. And the maximum chromatic dispersion that's tolerant for 1 dB penalty or 2 dB penalty. And you see that as bit rate increase, the tolerance for penalty decrease drastically. If this bit rate 4 times higher from 2.5 to 10G, or from 10G to 40G, so just 4 times as SDH hierarchy, 4 times. So question is, what's the relation between this number and the number, or this number and the number? Anyone? 4 times? Just 4 times, the relationship. Sorry? 4 times? I say that if you compare this 18,000 or something and 1,000 something, the relation of this number. Okay? Just 16 times. 16 times. 16. The bit rate increased 4 times. But dispersion penalty reduced to not dispersion impact of dispersion is not 4 times, but 16 times. 16. So that means a square of the 4. Square of the 4. As you can see, this relation is just 16. Just as you can see that not linearly the degradation of chromatic dispersion is not linearly increased with the bit rate, but so-called square of the number. Okay? So you may see 4 times bit rate increase, not 4 times, but 4 times, but 16 times degradation increase. Okay. And this is just chromatic dispersion coefficient and link length. So this table in handbook is just theoretical length limitation for a chirp-free narrow line with source at 65 nanometers for 1 dB penalty. So there are some applications called in the 1550 nanometers region. For example, intra-office less than 25 kilometers or 40 kilometers or 80 kilometers or 120 kilometers. So in NRZ 10G systems with ITUT G.6535 fiber, ISL and V applications, or with G.655 fiber for IS and L applications, are usually not limited by chromatic dispersion. This means, as you can see, dispersion coefficient for those fibers, 652 fiber has large dispersion coefficient, but 653 or 655 this fiber has less smaller dispersion coefficient at the region of this wavelength region. Yeah, so NRG 40G systems require dispersion accommodation for all fiber types for ISL and V applications. And for G.652 fiber, the NRG 40G length limitation starts only at a few kilometers. So you need something dispersion compensation if you use with G.652 fiber, because this has so large dispersion coefficients. This table shows that if your system is energy 10G, if you use G.652 fiber, you can transmit 61 kilometers. But if you use 653 fiber, smaller dispersion coefficient, you can transmit 333 kilometers and 116 kilometers for G.655 fiber. And this length drastically reduced for energy 40G signal, because we see that 652 fiber can permit only 3.8 kilometers transmission for 40G transmission system, and 653 20 kilometers, 655 7.3 kilometers. So this means ISL means so-called 25, 40, 80, 120 kilometers transmission cannot be used for 40G systems. Okay. And the only standardized line code or modulation format now is just NRZ and RZ format. And the impact of chromatic dispersion is also depends on the not only speed but also this modulation format, because the pulse width depends on this modulation format. As you see, RZ pulse has a narrower or smaller band signal waveform than NRZ format. But if we use RZ with a duty ratio of 50%, this means 50%, the tolerance, maximum chromatic dispersion tolerance reduces to 59 picosecond per nanometers, right? And if you change duty ratio of RZ to 2/3 or 1/3, this is so narrower pulse. The maximum chromatic dispersion, acceptable chromatic dispersion reduces to 39, the smaller. And this is mitigated by 78 for broader pulse. So RZ 40G, if you use RZ 40G signal formats, it's a very, very severe situation due to the chromatic dispersion. So next issue is that so-called PMD. So you must have learned about this PMD in chapter 1 or so, chapter 1 or 2, I don't remember. Chapter 1 or 2, and actually I told about PMD yesterday, chapter 6, briefly. So now I'd like to explain again about the PMD-induced power penalty. So as you see, that PMD is just caused by the, some asymmetry of the optical fiber in the core area. And if the fiber has PMD, the input signal path will split into two, roughly speaking, two polarization states in the fiber. And even if the transmitted signal is not so dirty or not degraded, at the output of the fiber, PMD means a delay between these two signals split into two polarization states, and the fiber has PMD, so the signal will split in two parts, and the synthesized power will have some broadened shape of such a signal path. So for 10G systems, you can see such a waveform distortion. Of course, this PMD is very significant for higher speed signals. For example, 40G. 40G has a so narrower signal path in time than 10G. Even if some clear eye opening, eye pattern, if you transmit the 40G signal through optical fiber, the 40G signal will split into such a pulse. So the effect of PMD is much larger than 10G. 10G has some tolerance because the 10G has originally a broad pulse, but 40G is a so very narrow pulse. So you will see a more drastic impairment due to such a PMD. So as a result, a larger waveform distortion. You can see this is just eye, very small eye. So you cannot accept such a distorted waveform as a receiver. And the terminology, differential group delay, is the difference in arrival times of the two polarization modes at a particular wavelength and time. That means the differential group delay is this delay between the splitted pulse, DGD. DGD itself doesn't change against the signal speed. This is the same for 10G and 40G. But the impact of DGD is different between the 10G and the 40G because 40G pulse has narrower signal path width. And the worst thing is that this DGD of the link varies randomly with time and wavelength. That means if this is the fixed value, you can compensate easily. But this DGD value change with time and wavelength. This means the optical fiber, the status will change in time because of temperature change or something like that. Yeah, this describes this situation. So if we measure DGD, this is the amount of DGD, picosecond DGD. And this is the wavelength. If you measure DGD by changing the wavelength of the signal, you will see, for example, such a blue line. You can get such a data. But as time goes by, this curve will change with varying with time, so black line or like that. So you can't fix any one characteristic of DGD because they change in time. So DGD ring varies randomly with time and wavelengths. This is called the Maxwellian distribution. So you can see the DGD only statistically, but the statistics of such a DGD variation can be understood by this Maxwellian distribution. So Maxwellian distribution you must have learned in chapter 1 or 2. Okay, and that contains a single parameter, which is the period of the PMD cohesion of the link, and the square root of the link length. Can be expressed that such a equation that the delta tau means the DGD, and this is the average value of delta tau. Okay, and the system impairment due to PMD at a specific time and wavelength depends on the DGD at that time and wavelength. So the power penalty induced by DGD at the receiver point R is a function of the relative power of the two orthogonal polarization modes. This means just as you saw that the two modes, the signal split into the two modes, and a function of relative power of the two orthogonal polarization modes. And of course, this varies as the relative alignment of the principal state of the polarization of the optical fiber cable and the polarization of the source varies. So this means if the polarization state in a fiber often changes with time or situation. And so the maximum link DGD is set to allow no more than a given power penalty in the worst case power splitting ratio. This means just the worst case is such a case that the signal power is split to equally to the two polarization states. As you can see the previous figure that if the 99% of the signal are split to one side and 1% split into the other side. But this is not problematic because this 1% contribution is very, very smaller, even we have polarization modus dispersion. And of course, the worst case power penalty is also affected by the transmission format. This means RZ format is more affected by the NRZ pulse because the pulse width is smaller than NRZ. And we say that's probability density of Maxwellian distribution, and the DGD distribute statistically along time or distance or wavelengths. And we say that this PMD is the mean DGD, maybe around here. The mean value of DGD, we say PMD. So in system design, we have to take care of this probability of DGD. So this means integrating the probability density function from delta T1 or given value to infinite value gives the probability of this time delay will happen, probability. And if DGD exceeds 3 times of the mean DGD, the probability can be calculated by this Maxwellian distribution. For example, 4.2 cross 10 to the power of -5 around here. So this means this probability is very small, the order of 10 to the power of -5. Actually, this table shows this calculated results of the probability of exceeding some max value. So as you saw, the ratio of max to mean is 3, the probability 10 to the power of -5, but the ratio will increase to 4, the probability decrease, so 10 to the power of -9. Like that, you can calculate the probability of the exceeding some value in a Maxwellian distribution. This is also so a penalty, PMD-induced penalty versus DGD value. So if you accept 1 dB penalty, PMD penalty, you have to keep your DGD value, for example, 0.3. And this curve depends on the signal characteristics. For example, receiver with signal-dependent noise or without signal-dependent noise. That means that this is maybe, I say, optical amplifier systems and no amplifier systems. That it depends on the system's noise characteristics. But anyway, this means that for the receiver without signal-dependent noise, this is 0.5 dB penalty for 0.3 time slots of the signal path. And for example, 0.1 time slot difference, this gives a 0.1 or 0.2 dB penalty for the signal quality. Okay. Yeah, next, roughly, basically the principle of PMD design. As I described, first, Q penalty, the DGD relationship is determined depending on the characteristics of the transmitter-receiver pair or modulation format. So you will design an acceptable DGD penalty value for the system, so assigned for the system. So you will set, for example, 0.5 or 0.3 dB acceptable penalty level for Q penalty. And as you see the DGD and the penalty, the graph, you can see acceptable DGD value, 0.1, 0.2, or something like that. And once you have acceptable DGD value, using this graph of Maxwellian distribution, you will set this acceptable DGD value, maybe small value. Okay? And this acceptable DGD value means that using, for example, such an equation, this is a system lifetime. In this system lifetime, you will set acceptable outage time, T. And this is the number of wavelengths. And this calculation of this probability of outage has to be smaller than this value. You set the outage time during your system lifetime. For example, you will permit only 5 minutes in a system life of 10 years. You will put here 10 minutes and 5 minutes and 10 years. So that this calculated results have to be smaller than 5 minutes divided 10 years. I don't know, but anyways, very small value. Okay, so we will design the PMD-induced power penalty like that. And this equation is so saying simple thing that if the DGD or PMD issues, if fiber or components, so many components have the DGD differential group delay in principle. So how to concatenate, how to design such a system, concatenation of many pieces of PMD include PMD-induced components. So this is just a simple equation that we will add the PMD value of each component, square root. This is an adjusting factor. I mean, as you see, the 3 times or 4 times of the mean DGD value. So DGD max per link can be calculated such the equation of square, summation of the square and the root square. This is just a calculation, same as the calculation of a Gaussian distribution, that you will add the sigma square plus sigma square, and you will root of sigma square, summation of sigma square in calculation of Gaussian distribution. Okay. Okay. So this is a DGD limit to ensure 1 dB penalty. So the DDG limits to ensure 1 dB penalty for the entire link are about 1/3 of the pulse width. That means if 0.3 times slot gives about 1 dB penalty of the system. So the value of the PMD not to exceed from outage probability with 5/9, for example, 5 minutes per year. Yeah? So the total PMD of a fiber link with total length L and PMD coefficient for the individual cable section is given by square root of length crossed by PMD. So, for example, a total link length of 400 kilometers for 10G signal if the PMD value is smaller than 0.5 picosecond per square kilometers. Okay, this is for 10. This is just a scaling law of the PMD coefficient. That means if PMD value is 0.5, 20 times equal to 10. And of course, if PMD value is smaller, becomes smaller to 0.2, you can increase the value 50 to 50. 50 means square 2,005 kilometers, 2,500 kilometers. Yeah, this is the square of the 20. This means 400 kilometers. Such a table available in the handbook. That's maximum link DGG for NRZ. For example, 1.25 to 40G pulse width is according to the signal bit rate, just 4 times, 4 times, 4 times. And this is the DGD limit to 1 dB penalty. Then you can calculate the PMD limit length. A PMD limit outage probability is less than 1 to the 10 to the power of -5. Okay? Just this corresponds to this value. Okay. So now I introduced the penalty by a chromatic dispersion and polarization mode dispersion. So do you have any questions? It may be difficult to understand so many things now, but you can understand later if you review back this slide, okay? The PMD is very, very difficult things in the optical transmission system. So it's very difficult for you to understand easily now, but you can understand later, okay? Any question? Okay.
What do you mean by penalty in this transmission? In the fiber optics? Penalty. What do you mean by penalty? Go, yes.
You need -20 dBm received power to match your requirement. For example, -20 dBm power, received power. But due to the fiber propagation, the waveform could be degraded. So to assure the same performance as this clear eye pattern, with this degraded waveform, you have to increase the signal power from 20 dB to, for example, -90 dBm. Because this is so noisy or dirty waveform. So you have to pay more money to get the same situation. So you may say penalty. Okay? Do you understand? So this is a so-called 1 dB penalty, we say. So if no waveform distortion, minus 20 dBm received signal is okay to meet the performance of VR of 10 to the power of minus 12 or something like that. But if you get such a dirty waveform or degraded waveform after transmission of fiber, fiber transmission, you will need more power, minus 1 dB more power than this clear wave. You say 1 dB, 1 dB penalty. Okay? Just the same meaning as your penalty. You do something wrong, you have to pay penalty. So this case, something wrong with the waveform distortion, degradation. Okay? So we will have some time for a coffee break, so I will continue a bit. So the next issue is refraction, impact of refraction, penalty due to refractions. It may not be difficult about what is a refraction, very simple refraction. But the refractions are caused by refractive index discontinuities along the optical path. So system performance degradation could be their disturbing effect on the operation of the optical source or amplifier. As I said, not only the passive component, but such an active component could be impacted by this diffraction or disturbed by the diffraction. So we have to keep the refraction to a lower level. So another effect is multiple refractions, which lead to interferometric noise at the receiver. This is just the so-called reflection-induced penalty. And the reflections from the optical path and paths are controlled by specifying, for example, the minimum optical return loss of the cable plant as a source reference point MPIS or connector, the maximum discrete reflectance between source reference points and the receiver reference points. This is just just saying reduce the value of reflection. This could be caused by the connectors or something like that. Okay, any single discrete reflection points. This is just simply optical return loss is defined by the ratio of the incident, so input optical power to the total returned optical power from the entire fiber. So including both discrete reflections and the so-called distributed backscattering as a Rayleigh scattering. Yeah? The Rayleigh scattering, you cannot suppress Rayleigh scattering because this Rayleigh scattering is a very basic nature of optical fiber. And this cannot be so impacted on the system penalty so much because this is just not forward, but just backward diffraction. And sometimes this Rayleigh scattering is a useful tool for measured optical transmission systems because you may use OTDR, optical time domain reflectometry. The OTDR rely on this Rayleigh backscattered light. So you can check the fiber length or fiber break by OTDR. Oh, sorry. So this is a description, the minimum optical return loss. So for the purpose of reflectance and return loss measurement, point MPI-S or MPI-R assumed to coincide with the interface of each connector plug. So this is described in G.6957. Actually, not the actual performance, that reference point of the reflection. And the minimum return loss will be limited to 24 dB, but some interface it is 14 dB. This could be a so old interface. So normally we will rely on this value. idea is just remove the connector point and directly connect by the fused splice. Fused splice has less deflections, as you know. And the maximum discrete reflectance is now limited to 27 dB. Okay, this is the end of reflection issue. So I would like to have a coffee break now. But do you have any questions now? No? Okay. So let's have a coffee break. So 20 minutes, okay? So let's convene 10:40. 10:40, okay? Okay. So thank you very much. This is a diagram for a multi-channel, multi-span optical system with the relevant interfaces. This is just not a single span, single channel system, but multi-channel, multi-span system. So we will have many reference point MPI, but mainly I describe MPIS and MPIR. So the power budgets of such a system are described in G.698.2. So the first of all, the most important parameters in an optical amplifier system is so-called OSNR, optical signal to noise ratio. This means that in an optical amplifier systems, the signal from transmitter will be decreased by the fiber attenuation and increased by the optical amplifier, but amplifier generates ASE noise. So at each amplifier, the noise will accumulate, and you can see this spectrum, that's the original spectrum, but noise will accumulate. So optical signal to noise ratio means this signal level to noise level. So as you can see, the noise level will rising up on the spectrum, and OSNR value will decrease. So OSNR is given by such equation. This is a signal power, and this is a parameter concerning the optical noise amplifier noise figure, and this is gain of amplifier. This is just a physical parameter, and the number of amplifiers. And this is a band of measurement bandits. In other words, this is a noise figure of amplifier, gain, and the number of amplifier. As shown this figure, OSNR degrade with NF value, gain of amplifier. This is the repeater spacing, and the number of amplifiers. So the in the budget, there is not minimum receiver sensitivity. This is because the receiver sensitivity is not important in this case because most main noise source is optical amplifier noise. But criteria is also same as 10 to the power of minus 12. So OSNR design, what does mean OSNR design? The minimum mean channel output power is given to ensure a sufficient high acceptable OSNR. So we say minimum OSNR have to take account the noise accumulation of the optical amplifier in the rings. And the maximum optical path OSNR penalty is defined as so lowest OSNR receiver side and the lowest OSNR at sender side. The penalty includes so many things like dispersion or PMD or something like that. So we need a suitable margin have to be allocated for multi-channels, such as multi-channel, multi-amplification systems. And so the maximum mean channel output power is given to limit the nonlinear effects and the consequent penalties. This is a principle of OSNR measurement. Basically, OSNR can be measured by using optical spectrum analyzer because noise and signal can be measured by a spectrum analyzer. So this, you will see on the spectrum analyzer, this WDM signal only depicted the 2 channels. This is a signal peak, and this is a noise level. So OSNR is defined by this difference between the signal power and noise power. The OSNR in theory defined as this peak power and this noise level. But as you can see, you can't measure directly this level of noise because of the signal. So we will use such a technique that this point apart from signal level, signal wavelengths, slightly different points to measure noise level and average this level, assuming that's a linear interpolation. And we can measure the OSNR directly by using the optical spectrum analyzer. And this is the same equation as shown in the previous figure. And this is OSNR calculation formulation, but you don't need to remember this in detail, just described on this handbook. So this means OSNR is in log scale, P out minus loss noise figure, and number of amplifiers. And this is just a booster amplifier case. But if booster amplifier and line amplifier is the same, this times is just 1. Same one and just 1. And minus log H nu. And nu F means this reference bandwidth, typically 0.1 nanometer. This is the measurement bandwidth or the noise level.